Several years ago, in the early 80s, I got a call from the exploration manager, come down to his office, and we had bought some properties. I think they were from Tenneco, and they had drilled this well. And he knew that on a previous company I'd worked for, I'd done a lot of work on this Chester formation, and he called me down to look at the well. And if you look at the porosity, there's no PE on this, but notice the neutron density is the same. And it gets up to 18% porosity. And that's pretty typical of a really good Chester well. One of the odd things is, and the RW is very well known in the area, there's no SP response. And you're running the RMF almost 10 times what the RW is, but there's no SP response. The big difference is, look at your scale, that's 1 to 10,000. And the resistivity, well, I can't see the red marker, but if you look carefully on that, it gets up to 2,000 ohm meters. And I said, I've never seen anything like that, Ed. So the problem is induction logs, lower accuracy above 150 ohm meter because the repeatability deteriorates because you're measuring such a small thing at that point because you're measuring conductivity in a very resistive rock. So that's a problem in this rock, and I'll show you a better way to do this later. When we looked at, this isn't from the original work, but we looked at the water saturation, and notice the water saturation is well under 5%. And the other thing, we can't calculate an RXO here because the deep is greater than SFL, and that the formulas we use are invalid. So we're using the shallow resistivity with the R sub Z, that's the mixed water. I'll show you a slide on that. And so that's our resistivity porosity. And look at the difference between it and the neutron density porosity and the sonic, which are about the same since it's all matrix porosity. And we've got resistivity under 2%. This is just what we're measuring. This is how you calculate R sub Z. It's because SFL is reading outside or deeper than the flush zone. Oh, excuse me. All right, so I couldn't, as I was sitting there looking at this log with the geologist and the exploration manager, I remembered something that Tony Messinio from the Arco well logging school back in the 60s. And he said, and this isn't exactly a quote, so I didn't put quote mark, SW less than 5%, call me, that's Tony, and possibility that it's oil wet. And so I told Ed, I guess it's oil wet because I really don't know, but it sure fits the pattern. So let's take a look at an analysis of this now. All right, well, first of all, let's just use the water saturations, which are not correct, of course, and see what we get. So we get an original oil in place of 726,000 barrels of oil, which is obviously way too high. And if we look at mobile OIP, and this is on 40 acres, that's the space in it, and you assume it's water wet, so the residual oil saturation should be somewhere around 30%. That's over 500,000 barrels of mobile oil, which is utterly ridiculous. So let's go on and see if we can get something reasonable. This is the water saturation using the conductivity equation from Monneron to 2007 SPE paper 105041. And I'm going to change it into resistivity, but the formula then is SW is equal to RW over RT to the 1/2 plus that correction. And that correction he recommends is a value of 0.07. That's literally a bulk volume water, is all he's adding there, of 0.07. And that's what's recommended for strongly oil wet reservoirs. And then you divide it by the neutron density porosity. So let's do that. And when we do that, you'll notice on the extreme right corner of that, we're getting reasonable water saturations now. And we still have the problem of the accuracy of the resistivity, of course, in this. So let's use that Monneron equation, and we're going to get an OOIP of over 400,000 barrels of oil, and that's kind of reasonable for this reservoir. So let's do a mobile oil. Let's just assume it's water wet, and that would give us 177,000 of mobile oil, which is a reasonable value if it was water wet, which it is not. So let's go in now and do it the right way. So the OOIP at 400,679 barrels of oil, that's using the Monneron equation. And then we could also calculate the water saturation of the invaded zone in the second equation down, or SI, because it's really not SXO. And that would give us a mobile oil, oh my gosh, a little over 45,000 barrels of mobile oil. And that would give us a residual oil saturation not of 30% as an estimate of a water wet reservoir. It gives us a residual oil saturation of 47%. Well, there's a lot quicker way of doing that. And that's the famous Y method, developed by Doyle and Martin in 1954. And that is that Y, which you're measuring the amount of oil that has been moved during invasion. And so you don't need all those other things on there. It says Y is equal to R sub Z over SFL to the 1/2. If you have an RXO log, that would be RMF over RXO minus RW over RT to the 1/2. And then you put that into your mobile OOIP equation, and that's just 775H times Y times your 40 acres times your thickness, 18 feet, divided by a BOI of 1.2. And that would give, of course, you get exactly the same answer, but at 45,000, a little over 45,000 barrels of mobile oil. So we have an OOIP which is reasonable for this reservoir of over 400,000 barrels of oil, but we get a mobile oil of only a little over 45,000. The question is 45,514 a reasonable amount of mobile oil? The answer is in the examination of the Chester production. I ought to give you people a chance over here too. I can only use one slide projector at a time, really. All right, so there's the perfs that were done. And it IP'd pumping 130 barrels of oil, 187 MCF gas per day, and 148 barrels of water. Notice, of course, in an oil wet reservoir, you will always make some water because water's not the wetting phase. The cumulative production in 8 years was 30,546 barrels of oil plus 0.15 BCF. And at that time, it was producing, boy, this must have been done by an engineer, 1.66 barrels of oil per day, plus 44 MCF, plus 22 0.23 barrels of water per day. So you're about at your end of your production. They plugged it not long after that. So, oil wet reservoir conclusions. Resistivities are commonly much, much greater than 1,000 ohm meters. And so lateral logs, which can get resistivity reliably up to 40,000 ohm meters, are a better log to run. SW, just like Tony said, I should much less, but less than 5%, bulk volume waters of less than 0.01. And resistivity porosities, if you have an RXO log, Phi RXO or Phi SFL, are much, much less than your sonic and your neutron density porosity. Also, mobile OOIP using the Moran or the Y method are reliable, since they give you the same answer, are reliable predictors of the production potential. Now, the last slide is other ways, if we figure out we've got an oil wet reservoir, is laboratory derived saturation exponent, or N, and N is equal to the log of RT over RO divided by the water saturation. Another way to do it is use, if you run a dielectric log, you can get a dielectric derived SXO. Actually, you could also get an SI from that depending on depth of penetration, but to calculate saturation exponent. So your SXO EPT for the Schlumberger tool at least is equal to the dielectric porosity divided by your log porosity. And then N is equal to the log of F times RMF over RXO divided by the log of the water saturation from the EPT. All right, that's the final slide. Does anybody have any questions? Yes, Hal.
For the speaker.
Oh, yeah. I just saw hands waving.
You still have 12 more minutes.
Okay.
I worked for Tony for 15 years, and we taught the petrophysical school, and he would always show this kind of example, but it wasn't actually to define water wet or oil wet. It was the difference between lateral logs and induction logs. And we would always tell the class, we never told you to run just one resistivity tool. And we looked at induction logs and did histograms in a field, and we also ran lateral logs. And in the high end, the inductions are all over the board. We saw a lot of negative conductivities. So that point, I guess back then when we had lateral logs, you know, they had the Delaware effect, things like that. So we would always run two. So I like the point is that, you know, you really have to be careful when you start looking at saturations with an induction log, when you get above 150 ohm meters.
That's right.
And as a young guy, I had an opportunity to talk to Maurice Tixier and Bob Alger. And those guys said, you know, they wouldn't take induction logs above 54 ohm meters. So, you know, I think it's a good point that, you know, log analysis is important, but if you got bad data, it's not going to work. And I think that induction log is probably not just correct.
That's a good point, but we got reasonable answers with it, though. You know, I agree with you because it's the log. It's the wrong log to run in this. I worked in, I had a master's student who worked in the Caballo sandstone in the San Francisco field in Colombia. And in that field, it's a sandstone, and in that field, the pay, this is out without doing an invasion correction on it, runs about 100 ohm meters. But in certain parts of the field, it's oil wet and it's running sometimes over 10,000 ohm meters in it. So again, you're right, Howard, I couldn't agree with you more. It's a poor log to run in this.
Well, I think what happens is folks think logs are bad, but they are bad in places. And when we would run induction logs out here, we'd do 0 millimoles, but then we still had to correct because you can't have negative conductivity.
No.
And that's, that's important. And what I see is folks are just not looking at the data. And right now, we're using an RDeep, and that can be an induction log. They digitize. It could be an induction log. It can be a lateral log in the Delaware Basin. It could be a microlog as RT, or it could also be a signal log. So it's important to look at the data, and that's one thing you've done over your years. You've pointed it out, so we appreciate the help.
Okay, thank you.
Other questions?
Still have 5 more.
Well, I bet they don't mountains. All right.
Here's your chance to give George a hard time.
Yeah. Yeah.
If not, then George, thank you.
Okay.